Last video, we went over how to send data from one thread to another with the multi-producer single consumer channel. So we had thread A and B, and we're able to send data from B to A, but we weren't able to share data between the two. Well, we were able to pass ownership from B up to A, and we didn't have a way to send it back to B. So that's where mutexes come in when we're sharing data between two threads pretty consistently, or more than two threads. We've actually kind of done this before with in single thread programs with the RC ref cell pattern. So we have before in other videos we've done something like, or should I say, RC ref cell. And just to jog your memory, RC is a reference counter which allows multiple values to hold immutable ownership of the interior value, and this ref cell here is an immutable value, but through interior mutability we're able to change the value inside of the ref cell even though we only have an immutable reference to it. We're going to follow a pattern much like that in what we're going to do now. We're going to follow, instead of RC ref cell, we're going to do atomic reference counter, which is a thread safe reference counter, and then mutex, and then our value that we want to share across threads. So before we introduce the atomic reference counter, it's a good idea to just kind of get familiar with the mutex API. So much like a ref cell, we go ahead and create one with a value, and then in the scope here, what we've done is we've acquired the lock to the mutex here. That is, with this block, we're going to, or with this lock, we're going to block the current thread until the lock becomes available. Then once we have attained the lock, we're going to get a result type, which will unwrap to get the reference to the actual value 5. So we're able to use the dereference operator to change the value inside that num to 6. The reason that we have to unwrap it is because this could error out, and the reason that m.lock would error out is if there's another thread that's holding the mutex and it panics, and in that case we'd want to return an error here, and ultimately we're fine if we panic as well. It's also worth mentioning that through the implementation of the drop trait, as soon as we go out of scope here, this lock is released. So we don't have to worry about unlocking, or should I say releasing a lock, a mutex lock. That's taken care of for us once this once the lock goes out of scope. To share a mutex, you might be tempted to pass a reference to the mutex to each thread, but like we went over a couple videos ago, the compiler will require that any reference that we pass to the closure that's running inside a thread, those references must have a static lifetime, because we cannot guarantee how long the thread's going to run for. So if we had thread down here, thread spawn, and then we did something with our mutex here, like we got a reference to it, let x equals, or we'll just keep it the same, let m or num equal m dot lock dot unwrap. If we try doing something like this, then we're gonna get mad because we don't have we're not sure how long m is gonna actually live for, which is why it's a good idea to use a reference counter of some sort like this, because if you remember from our good old regular reference counter, the value that the reference counter points to is going to remain valid as long as there's at least one strong reference to the reference counter. The same applies for the atomic reference counter. So we could have multiple threads that point to a mutex, and that mutex will be valid as long as at least one thread is pointing to this atomic reference counter. We use the atomic reference counter instead of the good old regular reference counter because reference counter is not thread safe. You can try using it across threads and the compiler will get upset at you fairly quickly. So we're going to use atomic reference count for atomically updating the strong reference count to our mutex. So let's go over this example from the textbook real quick. We're bringing in our atomic reference count and mutex types into scope. We're also wanting to spawn threads. So we're going to follow the pattern we just saw here where we're going to wrap a mutex inside of a atomic reference count. These are our join handlers here so we can wait for all the threads after we've spawned them all. And we're going to create a new strong reference to our counter, and we're going to move ownership of this new reference into the thread with move. And after we have this strong reference within our thread, we're going to go ahead and call lock and acquire the lock on the mutex, and then panic if we're not able to do that. And what we're going to do with this new reference to the inside of the mutex, we're going to dereference that and add 1 to it. And then at the end of here, at the end of our thread, we release the lock automatically. We're going to do this 10 times, and then we're also going to push our join handlers like we talked about here, and then we're going to wait for all our threads, and we're going to print out the counter up here. We're going to dereference we got to dereference it in this case, and we're going to call the lock and get the value out of it. So this should print 10. If we go ahead and run cargo run, we get 10. That's it for this video. I'm just trying to keep these a little bit shorter. So that in summary, we went over how the atomic reference count can be used in conjunction with the mutual exclusion to share data across threads. Now, we could run into situations where we don't need to wrap mutex within arg, such as if this mutex was a static value, but that's not the case in this situation. So, and in many situations, it does make sense to wrap it in a atomic reference count and share it that way. Thanks for watching. I'll see you in the next one.